In this video, we're going to learn how to compute Laplace transforms efficiently because you don't want to evaluate that integral every time. We'll do one derivation from scratch just to see how it works, and then build a table of transforms and go over two key properties that you'll need to know. We'll finish with some step-by-step examples so that you'll know how to compute any Laplace transform. Let's get started. To compute the Laplace transform of a function, what we do is we multiply that function by e to the minus st, and then we integrate it from 0 to infinity. This transforms our function of time to a function of s. Let's compute the Laplace transform of the function f of t is equal to 1. This is the simplest possible function that we can take the transform of, and it will show us how the integration works. We need to start with the definition. The Laplace transform of any function f of t is the integral from 0 to infinity of e to the minus st times f of t dt. Now let's substitute in that our function f of t is equal to 1. In our integral, we're going to replace f of t with 1, so we just have e to the minus st times dt. Since the upper limit of integration is infinity, we have to write this as the limit as some constant b goes to infinity, the integral from 0 to b, e to the minus st dt. Now we can integrate. This gives us the limit as b goes to infinity, e to the minus st. We divide by whatever multiplies t, and that is a minus s. And then we're going to integrate from t is equal to 0 to t is equal to b. This gives us the limit as b goes to infinity. We're first going to put in the upper limit of integration, so we'll replace t with b. This gives us e to the minus s times b, all divided by minus s, minus, and then notice we have a negative right here, so this becomes minus a negative, so we get a positive e to the minus s. Now t is 0, so this is s times 0, all divided by s. Now this next part, I'm going to be a little casual, and I'm just going to replace b with infinity. So this is e to the minus s times infinity, all divided by minus s. E to the 0 is 1, so we have a 1 over s. Now let's look at this part right here. If we assume that s is greater than 0, then we get e to the minus infinity, and that term is going to go to 0. So we're left with an answer of 1 divided by s. And let's also highlight that s is greater than 0. That is called our convergence condition. Notice that our answer is in terms of s and not in terms of t. Instead of computing integrals like this every time we want to take a Laplace transform, we're going to use a table instead. I've listed in this table some of the most important transforms. Let's start with the polynomials. We have the Laplace transform of 1. That's the one that we just did. And then we have t, and then all the way down to t raised to the nth power. I think this one is the most important because you can use this one to get any polynomial. Now let's look at exponentials. The Laplace transform of e to the at is 1 divided by s minus a with the condition that s is greater than a. Notice that this is really similar in structure to the Laplace transform of 1. That seems a little bit surprising because an exponential function is really different than the function 1. But nevertheless, their transforms are really similar, and the s in the Laplace transform of 1 is replaced with s minus a, in the Laplace transform of e to the at. Let's now look at sine and cosine. I'm going to tell you how I always remember these two. It's not mathematical at all, but it's always worked for me. Notice that sine starts with the letter s, and the numerator of the transform has a k in it, and cosine starts with the letter c, and the numerator of its transform has an s in it. So I always remember that the one with the s is the one that doesn't have an s in the first letter, and that's cosine. So cosine has an s, and sine has a k. Let's now look at two key properties that we're going to need when we compute more complicated Laplace transforms. The first property is called the linearity property. When you're adding two functions that are multiplied by constants, the constants factor out, like the constant a and b, and then the sums split apart, just like this. The second property is called the translation property. When you have a function that is multiplied by an exponent, what happens is the exponential shifts the transform. S shifts to s minus a. We'll see how we can use these properties in just a minute when we go over our examples. We're going to walk through two examples where we're going to compute the Laplace transform of a function. To make things easier, I've written down a table of transforms that we can use along with the linearity and the translation properties. In example 1, we are going to find the Laplace transform of 3e to the 2t minus 5 sine of 4t. Let's begin by using the linearity property, and let's split our transform into two transforms. We can write this as 3 times the Laplace transform of e to the 2t. The constant just comes out in front, and then we have minus 5 times the Laplace transform of sine of 4t. We need to find the transform of this exponential function and then the sine function. To do that, let's go ahead and let's write down the general formulas that we're going to need. The Laplace transform of e to the at times f of t is just f of s minus a. So let's make a note here. In our original function, we can think of this as e to the at times 1. So our f of t is going to equal 1. Now let's write down the formula for sine. The Laplace transform of sine kt is equal to k all divided by the quantity s squared plus k squared. Now let's see what this equals. We have a 3, and the Laplace transform of e to the 2t is going to be f of s minus a, where a is equal to 2, and our f of t is equal to 1. So let's write down up here that the Laplace transform of 1 is equal to 1 over s. So our s is going to become s minus 2. This gives us 3 times 1 all over s minus 2. I think that was the hard one. And then we have a minus 5. Now we have k over s squared plus k squared. K is equal to 4. So we have a 4 in the numerator, and then the denominator is s squared plus 4 squared, so that's plus 16. This gives us a final answer of 3, all divided by s minus 2 minus 20, all divided by s squared plus 16. And there's our final answer. I always think the Laplace transforms are going to be easy, but there's so many details that go into finding each transform. Let's look at our second example. We're going to find the Laplace transform of e to the 3t times t squared. We're going to use a formula that we used in our first example, And that formula is the Laplace transform of e to the at times f of t is equal to f of s minus a. Our a is equal to 3, and then our f of t is equal to t squared. So let's write down that f of t is equal to t squared. We need to find the transform of this, so let's use the formula that the Laplace transform of t to the n is equal to n factorial all over s to the n plus 1. Using that formula, we can find that the Laplace transform of t squared is going to be 2 factorial, which is just 2, all divided by s to the 2 plus 1, so that's s cubed. Now we can go ahead and compute the Laplace transform of e to the 3t times t squared. Let's look right up here. This transform is f of s minus a, and remember that a is equal to 3. So let's write this as f of s minus 3. And then this is equal to our f of s. So all we have to do is replace s with s minus 3. And this gives us 2 all divided by s minus 3 quantity cubed. And there's our answer. And that's it. You've now seen how to compute some complicated Laplace transforms, and you should be all set to work through some similar problems on your own. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.